Hello everyone and welcome to this second part of the lecture on the introduction to Raman spectroscopy. We will briefly discuss some experimental setup for Raman spectroscopy and imaging, and then we will go a little more into advanced aspects of quantum theory of Raman spectroscopy. The original experiment carried out by Raman, the sunlight, white light source, was filtered with a violet filter and the light was sent to a scattering liquid. Then, in a 90-degree collection geometry, Raman was able to collect both the Rayleigh scattering and the Raman scattered light, and then he filtered with a green filter, a low-pass filter, in order to cut out totally, or almost totally, the Rayleigh light and observe the green light, the red-shifted light, that are the Stokes photons. And these were the photons of carrying information on the vibrational levels of the scattering fluid. In modern Raman spectroscopy, the light sources are typically lasers. Here there are a list of some common laser wavelengths typically used. We typically use argon in the green, helium-neon in the red, or otherwise there are some other near-infrared laser diodes. Light is focused on the sample compartment and the scattering is collected at different geometries. This is a 90-degree collection geometry and light is sent to a monochromator. A monochromator allows to disperse the different components of the Raman scattering, and detection is typically carried out by charge-coupled devices or photomultipliers. In modern implementations, Raman spectroscopy are typically coupled to microscopes. This allows to carry out Raman spectroscopy at the microscopic level. In this case, the laser is sent to the sample through a microscope objective. The sample is typically set on a microscope stage that allows translation and therefore allows for mapping. And the backscattering light is collected and passes a filter that rejects the Rayleigh light and then passes through a confocal pinhole and enters the spectrometer. The spectrometer is basically always the same. This is the image of the spectrometer that we have in our labs. It's composed by a microscope. You see here the glow of the laser light and the microscope objective. Then the backscattered light is sent through the monochromator and through the gratings that allow to disperse the different colors or components, and then detection is carried out by solid-state detectors. This is a CCD camera made of silicon and is typically used if you want to detect light from the ultraviolet to the near-infrared. You see here at 1050 it's basically completely blind. If we want to go more in the near-infrared, we have to switch to an indium gallium arsenide CCD detector that allows to go to 1.2 microns here, or a band centered in around 1.8 micron in extended indium gallium arsenide detection and goes down to 2 microns. This slide summarizes 4 of the mostly used laser wavelengths in Raman spectroscopy, named 248 nanometers DPV. This is a neon copper laser. 532 for the visible, this is a frequency double neodymium YAG, 785, this is a typical laser diode, and 1064 nanometers neodymium YAG. And for each laser we see that we have detectors made by different materials. In the deep UV and in the visible and in part of the infrared we can use silicon. Silicon detectors like CCD or silicon avalanche photodiodes, but also gallium arsenide photodiodes or single photon counting units can be used in this range, namely from 500 to 850, 900 nanometers. If we go to the near infrared, namely at 1064, then we need to use either indium gallium arsenide or germanium. Germanium allows us to go also beyond 1.5 microns. Raman spectroscopy in the near infrared is typically performed using a peculiar schematic for detection, that is Fourier transform. It is basically similar to what is done in infrared spectroscopy, but here we excite the sample through a lens or through a microscope objective with the neodymium-YAG laser, typically emitting at 1064 nanometers. The backscattered light goes through a Michelson interferometer that allows for spectral separation of the energy components, and from this, through some special filter and dielectric filters, the light is focused into a germanium detector. We see in this image, this is the compartment of the laser, okay, and then this is the Michelson interferometer, and then the light comes back and goes into the germanium detector. As we can see, this instrument can be coupled to a microscope that is shown in this image to perform Raman mapping. Fourier transform Raman spectroscopy is particularly useful and important on fluorescent samples. This spectrum here is the fluorescent band of some nanocomposite materials shown, the optical image is shown here, in which we have mixed the graphene nanoplatelets into an epoxy resin. We see that if we excite it at 633, that is in the red or the visible, we just see a fluorescent band. So we don't have any fingerprint of the vibrational peaks. If we instead excite the sample at 1064, that is below the absorption band of these materials, we can see the Raman peaks of graphene coming out. So there is a huge advantage of using near-infrared light when the samples are fluorescent. In the market nowadays, there exist very compact Raman spectrometers like this one. This is from Horiba. And they are basically made by a microscope on top of which there is the spectrometer that consists of the, here in this part here, of the gratings to spectrally separate the light, and here is the CCD detector. Among the applications of Raman spectroscopy, materials precognition is one of the most important. As you can see here, these spectra are made on different plastics, starting from PA6 to PMMA to PVC down to polyethylene. We can recognize the different materials based on the position of the peaks, and of course we can assign with these peaks to the vibrational degrees of freedom of the molecule. For what concerns PE, for example, we have the 1450 cm2-1 mode that is assigned to CH2 cysteine vibration, then 1429 is symmetric deformation, 1408 is bending, and so on and so forth. One of the most important features of Raman microspectroscopy is the capability to perform maps that are chemical maps in which samples are mounted on piezoelectric tables or motorized tables that allow the sample to be scanned below the focused laser beam, and point to point some spectrum is acquired. We show here the optical image of a sample consisting of a glass substrate on which some metal nanoparticles or optical nanoantennas have been grown and on which some probe molecule is deposited. If we acquire spectra at different points, in this case here in glass we see basically nothing, while here we see the enhanced signal of the probe molecules. In our case this is methylene blue. What we can do is to set this energy, so observe which is the distribution of the emission at this energy. This is the Raman map at 620 cm2-1, coming out with this kind of image that tells us that in this zone we have the optical nanoantennas plus the molecule, while in this zone we do not have any enhanced signal, and this is basically glass. So this is a typical example of a Raman map that allows to carry out chemical mapping of samples. In this final part of the lecture, I will describe some advanced aspects of Raman spectroscopy based on the quantum mechanical picture. The classical theory of Raman spectroscopy has some drawbacks. In premise, it is not able to explain the intensity difference that we see between Stokes lines and anti-Stokes lines. Secondarily, there is no explanation for the discrete rotational spectra. In classical theory, rotations are continuous. There is no correlation between the Raman tensor and the transition electronic dipole moments, so electrons are totally uncorrelated with respect to vibration, while this is not the case in reality. And finally, there is no explanation of an effect that is called the resonance Raman effect, in which if we excite resonantly some electronic allowed transition, we see a strong enhancement of the Raman intensity. In the quantum mechanical description of Raman scattering, the molecule is a quantum entity. Molecular levels are quantized, while the electromagnetic field is still treated as a classical entity. And we move in the second-order perturbation theory. Let's see which are the main differences between the classical and the quantum approach. As we will see, there are several analogies. So first, in the classical approach, we have continuous variables. The position, the Hamiltonian, the frequency, all these quantities are continuous variables. While in the quantum picture, the variables are operators. We have wave functions and we have discrete levels. We typically start from an initial energy level of energy omega I and we end up to a final energy with energy level omega f. In the classical description, again, we have a dipole moment. In the quantum description, we have an analogous quantity of the dipole moment that is called the transition dipole moment. The transition dipole moment, as you will see here, is at the average of the dipole moment operator between the states, between the wave function psi and psi(f). This means that we have to carry out an integral, a volume integral of the operator p multiplied by the final state wave function, complex conjugate, and initial state wave function. In the classical approach, we have seen that we introduce a polarizability tensor that is time-dependent, and the polarizability tensor defines the induced dipole. In the quantum description, we have something analogous in the sense that we have a transition polarizability tensor here. We will see the expression in the next slide, and we can define and we can calculate the transition dipole moment as a scalar product between the transition polarizability tensor and the electric field, and this brings up an harmonic time dependence in which we have this factor omega L minus omega Fi. Omega L is the frequency of the laser that we use to excite the scattering process, and omega Fi is the energy difference between the final and the initial state. And omega L minus omega Phi represents the frequency of the scattered radiation. Again, in the classical picture, we have the radiated power, that is the time average of the second derivative of the dipole moment, while in the quantum picture, we have a transition polarizability, that is a time average of the squared root of the transition dipole moment. As we have seen, in the quantum mechanical treatment of the Raman scattering, the molecule is considered as a quantum entity. So it will have several states. The initial state, defined by a wave function psi and an energy omega I. The final state, that we will consider in our transition of wavelength of wave function pf and energy omega f. Omega fi will be the difference between these two energies and will be the energy of the transition that we will consider. But on top of this, there are also the other excited states that we will call pk, pk1, pk2 with energies omega k, omega k1, omega k2. The transition polarizability tensor in the second order perturbation theory writes like this. It's the sum of two components, and each component has numerators and denominators. What is important to note here is that in the second order perturbation theory, the transition occurs is a two-step transition. Actually, what we see is that this term can be considered as an absorption from the initial level to the first excited state. This is multiplied by this other term that represents the emission from the excited state to the final state. So the transition from the initial to the final state occurs through an intermediate state, and this must be summed over all the intermediate states. Here, omega ki is the energy difference between the excited states and the initial state. Omega kf is the energy difference between the excited state and the final state. Gamma k is the width of the state, phi k, which is much smaller than this energy. This is related to the lifetime of this energy level. Omega photon is the photon energy, and the only assumption that we are making here is that the photon energy is much larger than vibration and transition energy. That is, omega photon much larger than omega fi. The transition polarizability tensor describes all the scattering process that we have seen in the classical approach. That is, the Stokes, the anti-Stokes, and the Rayleigh scattering. Let's see how this happens. Again, we have a molecule with an initial state, a final state, and some intermediate state. If the energy of the final state is larger than the energy of the initial state, we will have a transition from the initial to the final state with the emission of a photon that has an energy slightly smaller than the excitation energy. Okay? And this is Raman-Stokes. If the final state is the same of the initial state, we will have the Rayleigh scattering. So the photon emitted will have the same energy of the incident photon. Finally, if the final state energy is lower than the initial state, we will have the anti-Stokes emission, in which the photon emitted will have an energy slightly larger than the incident photon, coming from the energy of the vibration. In the Stokes anti-Stokes cases, again, the photon energy will bring information on the vibration and the energy of the vibration. Up to now, we have only assumed that the photon energy is much larger than vibrational transition energy. But very interesting things occur depending on the fact that this photon energy is much smaller of any absorption transition, or if the photon energy equals to one of these absorption transitions. Let's see more specifically. Let us assume first that photon energy is much smaller than any possible absorption transition. So we have a photon energy that brings our system from the ground level to some intermediate level. This is what is called the normal Raman scattering. In normal Raman scattering, the system is brought to a so-called virtual state, and then it's brought back to the V equal to 1 energy level. The virtual state is a state of the distorted molecule. It is not a stationary solution of the molecule in its equilibrium configuration. In this case, as we see here, the denominators omega ki minus omega photon is basically equal to omega ki, and this occurs also for this second term. And since omega ki is much larger than omega photon and much larger than the width of the state, the transition probability is very small. So in normal Raman scattering, the transition probability is typically very small. The two terms are basically equivalent. Different is if the energy of the photon is capable to bring our system to some excited real energy level. In this case, we have some absorption, so the system is brought to a real state, and we have the so-called resonance Raman scattering. What happens is that since omega photon is equal or similar to omega ki, this first term is prevalent, since this sum is basically 0, and this means that this denominator will be dominated by this term, I, gamma k, and since gamma k is much smaller than omega photon, this will induce a very large, some enhancement in the transition probability. The second term is, in this case, negligible. Only the first term is resonant. So if our photon has an energy that can match at least one real transition, the signal, the Raman scattering, will be very much largely enhanced, typically 2 or 3 orders of magnitude. In this case, we have a real state that is an eigenstate of the molecule in its equilibrium position. The drawback of resonance Raman scattering, as we will see in the next slide, is that we can have fluorescent emission, which is usually much stronger than Raman scattering. We have seen so far that if the photon energy is much smaller than any absorption transition, we will have normal Raman scattering, in which the signal is very weak. We can see here on molecule like benzene or toluene, the experimental Raman scattering cross-section is of the order of 10 to minus 30, 10 to minus 29 centimeters square over steradian. Conversely, if the photon energy matches one of the absorption transitions, we will have two competing effects. The first one is the combination of absorption plus fluorescence, and the second one is the resonant Raman that we have discussed so far. Absorption and fluorescence are first-order transition, so the cross-section is very high. For this kind of dyes, we will have cross-sections of the order of 10 to minus 16 centimeters square, so we'll have a very strong signal. On the other hand, the resonant Raman scattering is a second-order transition, and so the signal is much weaker than fluorescence. We see here the orders of magnitude are of the order of 10 to minus 26 centimeters square, so over steradians. Here for crescent violet, we can see that if we tune actually the wavelength in order to be resonant, we will have an increase of the signal of basically a factor of 1 order of magnitude here, 568. For rhodomine 6G, we have almost a factor of 30 here between non-resonant and resonant condition, but we are still in the order of 10 to minus 24 centimeters squared over steradians, which is much smaller than fluorescence. So even if we are able to perform resonant Raman, the signal will be much smaller than fluorescence. There are basically two strategies to extract the resonant Raman signal from fluorescence. The first one is time-resolved Raman spectroscopy. It is based on the fact that resonant Raman scattering occurs on timescales of femtoseconds, that are the typical times of the adjustment of the electronic cloud, while fluorescence, that is spontaneous emissions, occurs on timescales of nanoseconds. So if we are able to collect the photons, the Raman photons, before the onset of fluorescence, we will get a signal that will be Raman signal, not fluorescence. On the other hand, we can exploit the fact that some molecules feature absorption in the ultraviolet and emission in the visible. So we can perform deep UV Raman spectroscopy and exploit the fact that Raman photons are close in energy to the excitation radiation. So in this case, if we excite in the UV, the Raman photons will be in the UV, while the fluorescence will be in the visible. So we expect to have spectrally separated Raman information and fluorescence information. To better understand the Raman selection rules in the quantum picture, let us first analyze what is called Born-Oppenheimer approximation. Up to now, we have considered the wave function of the initial and of the final states as some functions that englobe and involve both the nuclei coordinates and the electronic coordinates. But we have to see that the electronic and the nuclear motions occur on very different time scales. This given, we can separate the electronic and the nuclear wave functions in this way. If psi I is the wave function of the state I, this can be factorized as the product of an electronic wave function times the vibrational wave function. Here, nu I is the vibrational state quantum number and EI is the electronic state quantum number. As well, the energy of the state I can be written as the sum of an electronic level energy I plus the vibrational energy level I. If we do this, the transition polarizability tensor between the vibrational states nu I and nu f can be written in this way. So it's going to be the average between the states nu I and nu f of this quantity that can be considered as an electronic polarizability tensor, in the sense that this will only depend on the electronic states of the molecule. And of course, since the electronic wave functions will depend on the position of the normal coordinate q, alpha will depend on q. This can be done if and only if the final electronic state is coincident with the initial electronic state and is coincident with the ground state, if the energy of the electronic state is much larger than the photon energy, and this is as well much larger than the vibrational transition energy, so if we are dealing with normal Raman spectroscopy, if alpha is only a function of the nuclear coordinates q, and if the ground electronic state is non-degenerate. It is interesting to write this expression in this mode, since we can approximate the electronic transition polarizability tensor in this way: a steady state component plus a component that depends on the normal coordinate qk, summed on all the normal modes k. Born-Oppenheimer approximation, therefore, we can write the transition polarizability tensor as the sum of two components. The first one will involve the scalar product between the final vibrational energy wave function and the initial vibrational energy wave function. This, of course, describes the Rayleigh scattering, since this term is non-zero only if nu f equals to nu I, plus a term that contains this quantity. And since nu f and nu I are harmonic oscillator wave function, this term will be different from zero only if the difference between nu f and nu I is plus or minus 1. This dictates the selection rule for normal Raman spectroscopy, assuming an harmonic oscillator potential. If the oscillator potential is no more harmonic, so if we include anharmonicities, we will have higher order terms in this position, and this will lift these selection rules, allowing for transition between states in which the quantum number differs by 2 or 3. Finally, let me highlight how the quantum picture describes the temperature dependence and the difference in intensity between the anti-Stokes and the Stokes photons. In order to have a transition from a ground to a fundament to a first excited state, of course, the element of matrix must be the transition polarizability element must be different from zero, but the intensity of this transition will be also proportional to the number of molecules that lay on the ground state. As well, for the anti-Stokes, we will have nu equal to 1 to nu equal to 0, and so the transition will be also proportional. The probability will be also proportional to the number of molecules laid on the state 1. But these numbers are dictated by Boltzmann distribution, according to which the population of the level with energy E nu is proportional to the exponential of minus E nu over kBt, where kBt can be, for example, the ambient temperature kBt, that is equal to 208 centimeters to minus 1. If we assume this, we understand immediately that the anti-Stokes process is less favored with respect to the Stokes process, simply because the number of molecules that at thermal equilibrium will lie on the state equal to 1 will be smaller than the number of molecules laying in the ground state V equal to 0. And the ratio will be proportional to this term here. So the quantum picture can perfectly explain why the anti-Stokes lines are much less intense than the Stokes lines, and this ratio goes smaller and smaller as the energy of the mode increases. A lot of the materials shown in this introduction to Raman spectroscopy has been taken from these bibliographic resources that I suggest to read.